All right, so welcome back from spring break. Our spring break is, a little later in the semester than some school spring breaks. So we have a pretty quick turnaround. We have basically 2 instructional weeks and then the final. So um, the plan for today is to finish up the last little bit of chapter 7. I'm going to post a supplemental video on bootstrapping, this little kind of almost like appendix to chapter 7. I think it's an important aspect of developing confidence intervals, especially these days. It's kind of in a sense, a computer simulation based technique for developing a confidence interval. But we'll punt that to a supplemental video. And then we're going to start chapter 8 on hypothesis testing, kind of uh, our last big idea in the course. So hypothesis testing along with confidence intervals are the major two inferential statistical methods that we are going to talk about that kind of build off of our, in some sense, like first third and second third of the course material, the kind of data intense side of things, and then the kind of like abstract mathematical side of things, and bringing those two together to help us answer more complex questions. Um, so we'll start chapter 8 hypothesis testing today. We will continue with chapter 8 on Wednesday, and we'll plan to finish it next Monday, a week from today. Um, I have an additional presentation on some cautions and pitfalls of hypothesis testing. The interpretation and analysis of hypothesis testing is actually uh, perhaps the most challenging part of it, but certainly a non-trivial part of hypothesis testing, and that's what we'll talk about there. And that'll kind of wrap up what you might call like the major material for the course at the end of chapter 8. And then we have a few other little pieces. All of the pieces from this point on, we're just going to kind of scratch the surface of these are important ideas in certain fields. And really the goal is to have a few expository lectures for these ideas. So this way, if you go into, say, a finance course, or you maybe go into a psychology course and you see one of these come up, you can say, oh, okay, I recognize what that is. You have a firm enough basis that you can maybe understand what they're talking about and maybe use that as a jumping off point for further study. So those last couple of topics are correlation and regression, the chi-square test for goodness of fit and independence, and the analysis of variance, or ANOVA. I also do plan to post supplemental videos on the chi-squared and ANOVA chapters, uh, the basically next week, I suppose. Um, I think that should be like 4/20/28 actually, right? So a week of 4/28. And then we have our final exam week coming up before we know it. Um, the final exam will be posted and made available Friday, the 2nd. So that's actually a couple of days before the official start of the final exam week. However, with with remote and online classes, I do try to give you as much flexibility as I can because I know that folks often take these courses because they have logistical constraints. So this gives you kind of a full weekend if weekends work best for you. And that's also why, you might notice that the first day that the final exam is available is actually earlier than our last class meeting day. So that's why I'll have these supplemental videos posted early. That way, if you do want to take the final exam a little bit early, you're welcome to. But of course, you don't have to. You have until the end of that final exam week up through Friday the 9th. It's not comprehensive. It's only going to be on chapters 7 through 12. So the material that is from confidence intervals on. And I'll post a little more detail about the exam, as we get closer, but it'll basically feel like the previous exams. Be very similar format. It'll be 2 hours instead of an hour 40, but very similar format and all that. Okay, so that is our rundown for the rest of the course for the last couple weeks here. The quote of the day, oh, my window is a little misaligned here. Let me adjust this. There we go. The quote of the day is this statement: luck is when preparation meets opportunity. So, somebody might say, oh, it was so lucky that I walked into my final exam and I had just studied this topic the night before, and lo and behold, there it is, it's question one on the final exam, and I aced it. Well, was that lucky? Or, if that's the only section of the material you studied, I suppose then that would be quite lucky. But if you had been diligent in studying and you had studied this material and now you understand it really well, was that just that you were well prepared? Um, so, you know, uh, opportunity comes around from time to time for everybody. And if you're prepared to seize the opportunity, if you've done the preparation, if you've done the difficult legwork to put yourself in a good position, when that opportunity comes around, you can seize it. Um, if the opportunity comes around and you don't have the preparation, then it passes by. And so what we often call luck um, is really determined in a sense on our preparation. This is attributed to the famous Roman Stoic philosopher Seneca, Seneca the Younger, Lucius Annaeus Seneca. Although, uh, from as far as I can tell, I don't think there's much good evidence that Seneca actually said this or wrote this or something similar to this. So, not really sure where the quote comes from, but I think it's an interesting idea, and it's a phrase that's often quoted. Okay. I always think of that. Like, there was some person in human history that was like the first one to say this, and probably not Seneca. So like, who was it? Or some like random word that you look up in the dictionary. There was some person who was like the first one to say that word, or the first one to coin that idiom or something like that. And um, it's just interesting to think, I wonder who that person was. They're lost to history. Okay, so coming back to confidence intervals. Remember, the idea of a confidence interval has been a week and a half. So let's quickly recap. The idea of a confidence interval is this idea that we have estimators, we have sample statistics that are estimators of population parameters. Ideally, we would like to know the value of the population parameter, but effectively we never have access to that. So we're stuck with a sample from which we can derive a sample statistic. For instance, we can uh, take a sample, get a data set, and compute S squared, compute the sample variance of that data set. And that's an estimator of the population variance, sigma squared. We'd like to know sigma squared, and if we knew sigma squared, we would just say what it is and we'd be done with it. We wouldn't have to do any of this business. However, because we're essentially always stuck with samples and estimators, we say, okay, I mean, S squared is a good estimator of sigma squared. It's kind of like on average sigma squared. It's unbiased. Um, but how good is it, right? Is it like, I think that sigma squared is really, really, really close to S squared, or is it like sigma squared could be near S squared or it could be really far away? Is there a large variance in this estimator or a small one? Of course, we intuitively understand that the larger our sample size is, the better our estimator should be. So the closer to sigma squared, we would expect S squared to be. Uh, and as a side note, remember that, well, S, the sample standard deviation, isn't actually a quote good estimator of sigma, but for our purposes, we're going to say that it's good enough, and we'll kind of treat it similarly to how we treat the other good estimators. We did a little bit of work and we said that we come up with a confidence interval, in other words, a lower and upper bound, that we can compute on the basis of an observed value of the sample statistic. We get a data set, we look at the value of S squared, and maybe we might call it S squared observed. And we plug that into a computation, and I get a lower and upper bound. And what does that lower and upper bound tell me? What is the inference that I'm making? I'm saying, well, I'm something like, let's say, 95% confident that this interval from lower to upper bound covers the true value of the population parameter. That's really what our confidence interval tells us. It tells us something a little bit like, this is my best guess, and that these are my error bounds, right? So if I say, blank plus or minus some number, like is often reported in, say, the hard sciences like physics, chemistry, sciences like that, um, that's kind of along the same lines. Okay, so how do we do this calculation? Well, we do the calculation like this. We do n minus 1, sample size minus 1, times s squared times our observed value of the estimator, the sample variance, divided by this thing here. Previously, we had gotten, say, z indices maybe. We go to the z table, the standard normal table, and we get a number off of that. Maybe it's like 1.65 or something like that. Or maybe we get a t index, and that helps us to develop our confidence interval. Well, in this case, we just have a different distribution. When we're looking for a confidence interval for variance standard deviation, we use the distribution called the chi-square distribution. And again, I had posted these a couple of times before break. They're available on Blackboard, so you should have access to this table. I know that this is all pretty small to see on your screen, but presuming that you're kind of following along with a table on your side. But we have the chi-square distribution here, which is the appropriate distribution to use in this context. As a little aside, note that when we write something down here like chi-squared R or chi-squared L, we mean to take a number, like maybe this 2.180 off of the chi-square distribution, and that's the maybe entire thing that goes in the denominator. We don't like further square it. We don't take this 2.18 and then square it. The chi-squared right or chi-squared left is just a reference to the notation, the chi-squared distribution. So be a little bit careful with that. The chi-squared is just the reference to the distribution. We don't do a further mathematical operation of squaring it after we get it. We also had this idea of degrees of freedom, which happened to be n minus 1 in the previous instance when we were using the t distribution, and is n minus 1 again here. We'll see maybe coming up in future chapters. Sometimes the degrees of freedom is a little bit different, but it a lot of times has this kind of a feeling to it. Okay. And then once we get a confidence interval for sigma squared, this is where things get a little bit hand wavy, where we're kind of, accepting a little bit of, say, mathematical fuzziness here in exchange for simplicity. We can generate the confidence interval for sigma by taking square roots of everything. Let's go through a couple examples. Okay. So we did a couple examples of finding chi-squared numbers last time, and we talked about what the chi-square distribution is and all of that last time. But we're going to do a couple examples and then move on. Sorry, getting my writing pad set back up here. Okay. So in this example, we are interested in knowing the variance standard deviation of the masses of dollar coins. Sample of size 20 yields a sample standard deviation S equals 0.04111 grams. We'll assume normality, and we want to compute the 99% confidence interval for sigma squared and for sigma. A couple little notes here. Assuming normality, I didn't state this explicitly above, but it actually is quite important to assume an underlying normal distribution for the population for this confidence interval to be kind of reasonably valid. There are some approximations that happen, behind the scenes or under the hood, so to speak. And for those approximations for us to be confident that they're, good approximations, we need normality. The other interesting thing is that we're interested in variance or standard deviation. We actually see nowhere in here does the mean come up anywhere. It's kind of interesting. In the confidence interval for the mean, we saw the standard deviation come up, but in the confidence interval for the standard deviation, we don't see the mean come up. So that's kind of interesting. Okay, so let's work on this. Let's compute the confidence interval for the variance. Let me just copy this down here so that we have it in a place that's a little easier to reference. All right, so what's the first thing I need to do? Well, just like in the Z and T intervals, maybe the first thing that I'll do is I'll figure out what is my chi-squared number, because kind of once I figure that out, once I get my index from the statistical distribution, things are usually pretty easy from that point forward. It's usually just kind of a plug and chug. I have to plug things in, plug some stuff into the calculator, but this is usually the most challenging part. So remember that my chi-squared distribution kind of looks like this. It's not negative. That kind of makes sense because we know that variances and standard deviations cannot be negative. So it starts here at like 0, 0, kind of has a hump, and then tails off to the right. So this is my chi-square distribution here, 0, and it goes just off to the right. Now I need an upper and a lower bound. When I was dealing with Z or T, they were symmetric about their mean, but chi-squared is not symmetric about its mean. It's right skewed. It has this like infinitely long right tail, but the left tail, if you even want to call it that, just is cut off at 0. But we still would like to have some idea of symmetry here. In other words, I want a chi-squared index number that is associated with the lower bound and with the upper bound. We're going to call these, let me erase this little arrow here, get out of the way. We're going to call these chi-squared left and chi-squared right. And I would, so I don't have symmetry in my indices or in kind of the way that the picture looks, but I would like to impose a similar symmetry to what I had before. I need to choose these two values so that 99% of the area under the curve is between them. And that puts a total of 1% outside. And I would like to split that error, that 1% error, evenly between the two. So I would like 0.5% in this area, and I would like 0.5% in this right-hand tail to the right of chi-squared right. So my kind of my equivalent of the symmetry condition in the chi-squared world is splitting that 1% error, right? 1% of the time I construct a confidence interval that does not cover the true value of the parameter. I would like to split that error evenly above and below so that I'm not, on average constructing intervals that tend to be too high, or on average constructing ones that tend to be too low. So that when I make an error, it's kind of split evenly between my interval being too high or too low. Okay, so I kind of know now that chi-squared left is the chi-squared number with 0.5% area to the left, and chi-squared right is the chi-squared number with 0.5% area to the right. One thing that I might notice is on my table, what does my table report, my chi-squared table? It reports actually area to the right of the given critical value. So I need to consider areas to the right. Well, the area to the right of chi-squared right is 0.5%. That's an easy one. But for chi-squared left, it's more naturally associated with an area to the left of 0.5%. But I see the area to the right of chi-squared left then is 99.5%. So I see I'm going to be interested in, let me make my chi-square table just a touch bigger here. Okay. I'm going to be interested in this column with area to the right of 0.995. That's going to be where I'm going to find chi-squared left. And for area to the right of 0.005, 0.5%, that's where I'm going to find chi-squared right. Now, I also remember that I have degrees of freedom in the chi-square distribution. It's kind of like the t-distribution. The same way that, when we had like a standard normal, that was just one distribution, but the t-distribution, there were lots of like standard t-distributions. and it was parameterized by this idea of degrees of freedom. Same idea here. There's lots of something like standard chi-square distributions parameterized by these degrees of freedom. So which row am I looking for? I've identified the two columns I'm interested in, these two. But which row am I going to look in? Well, what are my degrees of freedom? I set up here my degrees of freedom were n minus 1, essentially for the same reason that degrees of freedom was n minus 1 in the t interval. So my degrees of freedom, n minus 1, or my sample size is 20, and degrees of freedom are 19. So I'm going to come over to my chi-square table. I'm going to look in the row corresponding to 19 degrees of freedom. And for chi-squared left, that number is going to be the one that's in the column corresponding to 0.995 area to the right. Or this gives me, right here, 6.844 for chi-squared left. And recall, this 6.844 is chi-squared left. We don't like square the 6.844. Chi-squared left is 6.844. In a sense, the squaring has already been taken care of behind the scenes. Remember, we build the chi-square distribution using squares of standard normals. So the 6.844 is what chi-squared left is. It is the number that goes in the denominator up here. And then chi-squared right has 0.5% area to the right, or 0.005 area to the right. So again, we are in the degrees of freedom 19 row here. And we're in the column with area to the right of 0.005, 0.5%. And this gives me a chi-squared right index of 38.582. So that number is chi-squared right. And the good thing is that from this point forward, it's actually pretty easy. So what is my confidence interval? Well, on the lower end, I have n minus 1. Well, that's just 19 times s squared times 0.04111 squared. I do have to be a little bit careful, make sure whether I'm given s or whether I'm given s squared for my sample data. I'm given the sample standard deviation 0.04111, so that needs to be squared here. And be a little bit careful on my lower bound. I'm dividing by chi-squared right. Because it's in the denominator, the bigger one is associated with the smaller value. Right, so 38.582. It's not the end of the world if you get them backwards, because you'll immediately see that one of the results is going to be bigger, one is smaller. If you get them backwards, you kind of, it's a pretty clear indication that you got the chi-squared numbers backwards. So for my lower bound, that's what I have. And for my upper bound, I have the same thing, just using the other chi-squared number. And now I'll put chi-squared left in, the smaller number in the bottom gives me the bigger fraction. Let me start up my calculator here. And what do I have? 19 times 0.04111 squared. And that's divided by 38.582. Or this is about 8.3 times 10 to the negative 4. And if I do second enter to bring up what I just typed in, all I need to do now is change the denominator from 38.582 to 6.844. Choose to write that as 6.844 to just make the digits line up a little nicer. And this gives me 0.00469. Or what would that be? If I make this times 10 to the minus 4, it would be about, what, 47.0 times 10 to the negative 4. This is my 99% confidence interval for sigma squared. Now, a couple of things we notice. Number one is that the confidence interval for sigma squared, the formulas actually look nicer than the confidence interval for sigma. And actually, for the confidence interval for sigma, we also have this kind of fudge factor that we have to deal with here as well. So in some sense, mathematically, maybe the confidence interval for the variance is nicer. But the other thing that we might realize if we think about it is my units are actually square grams, right? Why am I getting these numbers like 10 to the minus 4 when the standard deviation that I input was like 4 times 10 to the minus 2? Well, because I'm dealing with the variance instead of the standard deviation. How do I get back to the standard deviation? Well, I just square root my answers for the variance. Or if I wanted to kind of start from first principles, I would do square root of 19. Now I'm doing square root of s squared, so that actually just gives me s outside. And then I have square root of 19 over 38.582. That's under the square root times 0.04111. Instead of squaring it and then square rooting it, I'll just leave it outside the square root. And then similarly, I have square root of 19 divided by my chi-squared number, 6.844. That's under the square root times 0.04111 there as well. Let me plug these into the calculator, clear these out. So I need 19 over my chi-squared number. So that's what's under the square root, and then I multiply by 0.04111. So this gives me 0.029, let's call it, for my lower bound. And then I'll do second enter. And again, I'll just change my chi-squared number from 38.582 to, to 6.844 to the other chi-squared number. So this gives me 0.068. This is my 99% confidence interval for sigma, the standard deviation. This is in units of grams, so it's in units that are consistent with our data up here. So that's why it looks a lot nicer. We can see that 0.04 is kind of, more or less in between 0.02 and 0.06. It's not quite right in between though, right? So my lower bound is, let's just call it about 0.03. That's about 0.01 away from 0.04. And my upper bound is, let's call it about 0.07. That's about 0.03 away from 0.04. So our kind of right side of the confidence interval is about 3 times as large in a sense as our left side. Or our, if we were to look at this interval visually, this is our lower bound, this is our upper bound, and our s squared is actually like 3/4 of the way to the left. Right. So our point estimate isn't in the middle of the interval, or our interval isn't symmetric about the point estimate. But that's because the chi-square distribution isn't a symmetric distribution. this also kind of makes sense, right? I mean, in a sense, like I somewhere down here I have 0, and that's like a hard line. It makes no sense for me to have part of my confidence interval hanging over into the negative side because I know that it's impossible for my population variance or standard deviation for that matter. I guess this really should be S, not S squared, but it's impossible. It's mathematically impossible for them to be negative. So why would I want to include a negative part of the real line as part of my confidence interval? My confidence interval was kind of biased away from the negative side because it's almost like, there's like two same poles of magnets or something that are like on the lower end of the confidence interval and on the, at 0, because I'm never going to have the lower bound of the confidence interval go below 0. That would be kind of like wasting a part of my confidence interval on an area that I know is impossible to achieve. So it kind of like intuitively makes sense, and it also mathematically makes sense given the right skewedness of the chi-square distribution. But we do see though that the point estimate is inside of the interval. The point estimate shouldn't be outside of the interval. That wouldn't make sense. It's inside the interval, but it's just not right in the middle of the interval. Okay, and let's go through example 2 here. So once more, let me copy this down. There we go. Okay, so example 2, a company produces a certain type of cookie. The machine is calibrated to produce cookie packages with a mean weight of 32 ounces and a variance of 0.015 square ounces. So because we're in variance, we're working with square units. Compute a 95% confidence interval for sigma squared on the basis of the following sample. So this is kind of like is my machine out of spec and I want to shut it down and recalibrate it type of question, right? So the sample is we take a sample of size 25 and we find a sample variance of 0.029. Now 0.029 is a bit bigger than 0.015, but essentially what we're asking here is, do we think that this 0.029 is bigger than 0.015 just essentially by chance, by sampling error, or do we think that there's something more systematic going on? That's kind of what we're asking here. So and we have a decision criterion that we set up for on the basis of some other reasons, going to be partially financial, partially maybe legal, right? We don't want to be sending out packages that don't contain the right amount of product. That's going to be false advertising if we do that too often and know about it and so on. So we decided that if either bound, the upper or lower bound of the confidence interval, is outside of this range, 0.008 to 0.030, then we'll shut down the machine for recalibration. Should the machine be recalibrated on the basis of this sample? Okay, let's check. So let's develop our confidence interval. So once again, the most challenging part is figuring out the chi-squared number, so let's start there. So I have a chi-squared left and a chi-squared right. I'm constructing a 95% confidence interval, which puts 95% in between the two. And I want to impose symmetry in the sense of having half of the error in each of the tails. So 95% of the time I'll construct an interval that does cover the true value of the population variance. But 5% of the time I'll miss. Half of that time, 2.5% of the error I want on the left-hand side and 2.5% on the right-hand side. Keeping in mind the fact that my table gives me areas to the right, I see that chi-squared right is indeed the index with 2.5% area to the right. But chi-squared left is the index with 2.5% area to the left, which is 97.5% area to the right. I also note that I have degrees of freedom, n minus 1, 25 minus 1, or 24. Okay, let me jump over to my chi-square table. I know that I'm looking for chi-squared indices in the degrees of freedom 24 row. And I know that I'm looking for areas to the right of 97.5% and 2.5%. So that's going to be this column and this column. These are kind of, if you see the table is kind of split in two right down the middle, there's actually a little dividing line at the top between the 0.9 and 0.1. These are like the middle columns of their respective halves. Okay, so I want the 97.5% area to the right column, the 24 degrees of freedom row, and that indicates 12.401 for chi-squared left. Again, remember that this is what chi-squared left is. We don't like square this and get, 150 or something like that, just 12.401. And then for chi-squared right, we're looking for an area to the right of 0.025 with, again, 24 degrees of freedom. And we see that intersection is right here at 39.364. So there's our chi-squared right. And again, at this point, we've got most of the hard work out of the way. It's now just mostly plugging things in and getting an answer out of the calculator. Okay, so my lower bound will be n minus 1, or that's 24, times s squared. My sample variance is 0.029, divided by, and now for my lower bound, for the smaller fraction, I put the bigger chi-squared number in the denominator, right? Bigger denominator, smaller fraction. That's my lower bound. My upper bound looks very similar, just with the other chi-squared number. I am being careful here, right? This is a confidence interval for the variance. I need to put in the sample variance, and the sample variance is exactly what I'm given. So I just put that 0.029 in as it stands, right? If I was given sample standard deviation, I'd have to square that, kind of like I did up here. So there is a little bit of, what I often call bookkeeping, just being careful with these little details like this to handle here. But we do just want that 0.029 by itself, not squared. If you were looking at that and saying, wait, why did we square this one up here? Because up here we were given the sample standard deviation. Just a little side note there. Okay, and then for our upper bound, we want the other chi-squared number, chi-squared left. The lower, the smaller chi-squared number going on the bottom gives us the bigger fraction, 12.401. And I can pop over to my calculator. I need 24 times 0.029 over 39.364. So that gives me 0.018 or so for my lower bound. And then I just need to change my chi-squared number to 12.401. It gives me 0.056 for my upper bound. This is the 95% confidence interval for the variance sigma squared. And then kind of as a segue into hypothesis testing, I have this follow-up question. So that is our confidence interval. That's, that wraps up that part. But then our question, if either bound is outside of 0.08 to 0.030, we'll recalibrate. Well, 0.018 is between those two numbers, but 0.056 is bigger than 0.030. It seems like our process is no longer properly in control. We have a number that's out of spec. We'll shut down the machine, we'll recalibrate it, get things back in spec, and then start it back up and start manufacturing product again. Any questions on anything in hypothesis test, or sorry, in confidence intervals before we move on to hypothesis testing? Okay, let me pause my screen share here really quick or actually let me switch my screen share. Switch it to just that one. Okay. I think I can actually close out a couple of these bits over here. All right. Okay, so moving on to our last, oh, okay, my screen is sharing now, right? Yeah, good. All right, moving on to our last major topic in the course. So moving on to hypothesis testing. Similar to kind of confidence intervals, where when we developed confidence intervals, we saw that really the math was quite familiar, right? We recognized it from like the central limit theorem in chapter 6 and from z-scores from previous work and so on. So it was fairly familiar, but we were using it in in a slightly different way, right? We had a different logic uh, that was driving the calculations. We're going to see a similar thing in chapter 8. The calculations themselves will usually be fairly straightforward. I mean, relatively speaking, of course, this is statistics. Nothing is super straightforward, right? But relatively speaking, the calculations themselves will be fairly straightforward. Maybe um, finding probability that z is less than some number or something like that. We know how to do those kind of problems from chapter 6, or um, maybe finding a z index or a t index or something like that. So these are problems that we kind of know how to approach, but hypothesis testing can actually be quite difficult. And the reason is that the logic behind it. So first, the reason that we do certain calculations and not other calculations, the reason that I, want to find this area and not some other area, can be a little bit complex. And then after I do that calculation properly and I get an answer, saying what that answer means, what the result of that calculation means, can also be fairly complex. We saw a hint of that in the confidence interval section, where we had to say something like, there's a 95% chance that an interval constructed in this manner covers the true value of the population parameter. And we did not want to say something like, there's a 95% chance that the population parameter is in this interval. They sound almost the same, but one is a frequentist statement and one is a Bayesian statement. And as I mentioned before, in confidence intervals, if you say it one way or the other, are you likely to mislead somebody? Are you likely to make somebody um, think a thought that is, somehow fundamentally untrue, or that they will like regret later on? Maybe not. It's maybe a little bit more of a technical detail in chapter 7. But in chapter 8, if you make a similar mistake, actually the answer is yes. It can be very misleading as to what the proper interpretation of the hypothesis test is. So that's why we wanted to be careful in chapter 7. Number one, because it just is, proper form, but number two, because in chapter 8, it's much more likely to be misleading. Okay, so to introduce the idea of hypothesis testing, and as a side note, I think I recommended before Easter break that you kind of take a glance through the first bit of chapter 8. And I recommend that you take a glance through it again after our discussion here. Getting this logic down is really the hardest part of chapter 8. The calculations, they can be a little bit tedious at times, but it's really the logic that's the challenging part. Understanding why we're doing what calculations at what times and so on. So I think the best way to introduce chapter 8 is actually with this narrative that I read in a stats textbook. It's kind of like a small textbook. I think it was published like 30 or 40 years ago or something, but this is, I think, the best way to introduce the idea of hypothesis testing. Then we'll again go through another kind of attempt at introducing it in a very non-mathematical way, just thinking about the logic behind it, using the analogy of a jury trial. And then maybe we'll work our way towards something that feels a little bit more mathematical, but maybe we won't fully develop the math yet. We'll just kind of get a gut feeling for it, and then maybe we'll finally take a crack at the actual mathematics. So I don't know how far we'll get today, but that's kind of the plan. So we're going to take a kind of a couple of runs through the logic where there's essentially no math involved before we actually develop the math, because I want us to be able to concentrate on the logic and not the calculations. All right, let me jump over to this hypothesis testing narrative. Okay, so I have this. Unfortunately, it's like a scanned image. Maybe I should actually just like type this up at some point and make it a little bit cleaner. And I mean, I could make my own version of it or something like that, but I feel like that would be almost like plagiarizing, because this is the only book that I've seen really have a nice dialogue like this. So I feel like this is really their intellectual property. I don't think this is something that's very common among lots of stats books or anything like that. But the reference for this is Friedman's Statistics from 1980. All right, so I'm just going to kind of read through this. And basically what this is a dialogue between a couple of folks just talking about some evidence either in favor of or against, some particular thing at their work. All right, so I know that it's kind of blurry, so I'll actually read it for you. I know that nobody's really a fan of having things that are on the screen read to you, but to try to make it a little easier for you to read, because it might not come across great on your screen, I will read through it. Okay, so the introduction here, was it just due to chance or something else? Statisticians have invented tests of significance, or hypothesis tests, to deal with this sort of question. These tests are among the statistical techniques most widely used in the social sciences, and that's very true. You open up a medical journal or a psychology journal, or for that matter, a finance or economics, any journal, or even an experimental physics journal, and you look at the article, I can almost guarantee that you will see a hypothesis test somewhere in there. Okay, almost impossible to read a research article in the social sciences without running across them. So let's find out what they mean. The main difficulty is in the language, and I think that's true to an extent, but really the main difficulty is in the logic. It's and what exacerbates that challenge is that we use language in imprecise manners most of the time. Me too. Most people most of the time use language imprecisely, but when we're in contexts like this, we have to be very careful to use language very precisely. So we have to shift our usage of language a bit. So here's an example of the problem. We see a statement like, with the one-tailed z-test, the null hypothesis was rejected at the 5% level. The difference must be regarded as statistically significant. This is actually a very precise 2 sentences, but the meaning is very obscured, right? Because there's so much jargon in here. Okay, so let's take a step back and look at this example where they're talking about this flex time that a company was implementing. So this let employees choose their their start and end times for the day within certain limits set by management. Okay, so I'll just start reading from this point forward. So, among other benefits, flex time is supposed to reduce absenteeism. Of course, a firm with many thousands of employees, keep in mind this is 1980, they didn't have, easy computer tracking systems, at least as easy as they are today back then. So of course, a firm with many thousands of employees might have a hard time studying all of them. So getting the population level data, uh, they might be stuck with a sample. So they're studying this on a sample basis. Suppose one firm knows that in each of the past few years, employees have averaged 6.3 days off from work, apart from vacations, per year. This year, the firm introduces flex time. Management chooses a simple random sample of 100 employees to follow in detail over the year. At the end of the year, these sampled employees are found to have averaged only 5.4 days off work, as opposed to the kind of standard that it seemed was 6.3. The personnel committee is now meeting to assess this result. Okay, so the investigator says, among other benefits, flex time reduced absenteeism. On average, days off of work dropped from 6.3 to 5.4 this year. Now, the person they're labeling the chance skeptic, so the skeptic who's kind of playing the devil's advocate here, says, okay, now look, your sample only amounted to 100 employees out of the 5,000 at the plant. By the luck of the draw, you just happen to get too many hard workers in your sample. All you're showing us is chance variation. In other words, this just happened by chance because you picked a small sample. And the investigator says, not true. Skeptic asks, what was the standard deviation in your sample? And the investigator says that days off averaged 5.4 with a standard deviation of about 3 days. Right? This is a very reasonable question to ask, because if the standard deviation is very large versus very small, that tells us something about how close we think the estimate is to the thing it's estimating. Except that doesn't tell us everything, which is what we're going to see here. So the chance skeptic says, well, the difference between 6.3 and 5.4 days is a lot less than one standard deviation. It's, say roughly a 1 day difference for a standard deviation of about 3 days, a 1/3 of a standard deviation. A 1/3 sigma event is not unlikely at all. So he says that looks to me like chance variation. It's not even a 1 sigma event. It's not unlikely to have occurred just by chance. But the investigator says, okay, well, let's think about this a little more. I want to make a calculation. I'm going to use a box model, which is one way that some folks introduce the idea of probability. So consider that there are 5,000 tickets in the box, one for each employee, showing the number of days taken off work. We drew 100 tickets at random from the box. What we really know for sure is these 100 tickets. Agreed, so they agree. What we're arguing about is the average of the 5,000 numbers in the box. And this, he's asking the skeptic, you still say that it's 6.3 days, and I say that it's gone down. The chance skeptic agrees. They say that the skeptic says that by the luck of the draw, you just got too many small numbers in your sample and your draw out of the box. So the investigator says, okay, we don't know the standard deviation of the box, but can we agree to estimate it by the sample standard deviation 3 days? Seems reasonable. Now, this is the first difference is, okay, so instead of looking at standard deviation, which is the standard deviation of one draw of a paper from the box, from the population, says, well, really what we ought to look at, they gloss over this a little bit, so I'm clarifying this, that what we really ought to look at is the standard deviation of the sampling distribution of the mean, the standard deviation of X bar, which is the standard error. So the standard error for the sum of 100 draws is square root of 100 times 3, or 30 days. So the standard error for their average, I don't know why they did it this way, but the standard error for their average, or the standard deviation of X bar, is 0.3. So could do it a little bit more cleanly by saying the standard error for X bar, is 3 over square root of 100, right? It's sigma over root n is 0.3. That's all that they did. you know, he was just noting that the sum is related to the average in this manner. And now he says, okay, suppose that you, the chance skeptic, are right, and the average of the box is still 6.3 days. Then you'd have to expect the average of the sample to be around 6.3 days as well. And actually, well, 1 unit, right? 1 unit difference on a scale of 0.3 is actually 3 standard errors. And this is really the important part here. So we have enough draws, we can use normal approximation and so on. We have a 3 sigma event, and this is really the crux right here. So he says you have a hard choice to make. Either you can kind of dig in your heels and insist that the average of the box is still 6.3 days, or you can agree that the average of the box went down. However, if you stick with the 6.3 days, if you dig in your heels, you need a minor miracle to explain our data, to explain away a 3 sigma event. That's like a 1 in 1,000 chance. So there's a 1 in 1,000 chance of being that far below the expected value. So this is really the idea is we have some data and we have a preconceived notion. The preconceived notion is, well, the mean time off has always been 6.3 days. We suppose that it's still 6.3 days. We have some evidence that is in conflict with that way of thinking. We have a sample mean of, what was it, 5.4 days that's below 6.3. And in fact, it's far enough below that to explain it with sampling error, it's theoretically possible, but it's only like 1 in 1,000 chance. If I had 1,000 different companies like this, only one of them would have gotten that result just by chance, and the other 999 would have gotten that result based on a systematic decrease in the number of days off. What makes more sense at this point? To dig in our heels and insist that the mean has stayed the same and just that something very unlikely has occurred, or to switch our worldview, switch our mentality and say, okay, I think that indeed the mean has gone down. The mean number of days off has decreased. And then the chance skeptic says, does this prove that flex time reduces absenteeism? And the answer is no, but we've provided evidence that absenteeism really went down. It might have been flex time that did it. It might have been, maybe it just wasn't as bad of a flu season this year. Maybe there was a confounding variable that came into play. Maybe it could be the case that if we picked a small enough sample, we might argue that it's not representative. So that could be a problem, right? Or if we picked a sample like all from the sales department or something like that, well, maybe our sales department just didn't, have the flu run through it this time, but maybe the manufacturing department did. Who knows? So there are other arguments that we could make, but we've provided evidence. We've provided statistically significant evidence, we would say, that absenteeism really went down. Okay. So that is really the idea. The real crux is that we want to look at how unexpected such a result would be if our original worldview stayed the same, and if it's quite unlikely to have occurred just by chance, and more likely to have occurred if the thing that we think happened actually did happen, that absenteeism went down, then we change our mind essentially. We switch from one point of view to a different point of view. So that's why it's called a hypothesis test. We have competing hypotheses, competing kind of possible worldviews, and we're testing which one we should go with. Okay, so let's again take a look at hypothesis testing via another analogy. This one's a bit more abstract. It's related a bit more abstractly. We won't really think of any numbers in this example. We'll think of a jury trial. So in a standard jury trial, in a, say, criminal trial for whatever crime somebody's been accused of, we have two possibilities for the person. We're going to consider that the laws and so on are set up precisely enough that if we were omniscient, if we knew all of the facts, we could cleanly determine the person's guilt or innocence, right? There's no gray area in the laws or anything under our setup here. Of course, in the real world, there's very much gray area in the law. So we basically have two choices. We have two hypotheses that are competing. The person is guilty, they did not commit the crime that they are accused of, or they're innocent. They did commit the, said that the wrong way. They're guilty, they did commit the crime they're accused of, or they're innocent, they did not commit the crime they're accused of. These are the two choices, right? So our question is kind of what is their actual status? Again, if we were omniscient, if we were all knowing, we would just like use our omniscient powers to figure out what all of the facts are. And we'd say, okay, they are either certainly guilty and call them guilty, or they're certainly innocent and call them innocent. And we wouldn't have any questions or any need for a trial or anything like that. But in reality, of course, we're not omniscient. Wouldn't things be so nice if that was the case, right? We'd all have lots of money from knowing exactly what stocks to invest in and all those kind of things. Um, Although I don't know, maybe I wouldn't want to be omniscient and like know what everybody is saying about me in their head or something like that. I suppose there are pluses and minuses. So in reality, we have to have a test of some sort. And in this case, this is a trial. And essentially, the purpose of a trial is to establish facts, to establish the facts of the case. And the jury, once those facts are, the jury decides which facts are established throughout the trial, and then how they correspond to the elements of the charge levied against the defendant. So if the facts of the case substantiate the charge, then the person is guilty. And if the facts of the case do not substantiate the charge, they're not guilty. For our purposes, at least at this first pass, we're going to suppose that the test, the trial, results in a claim of guilty or innocent. Really guilty or not guilty, but that's a nuance we're going to handle in a couple minutes here. Okay, so what do we have? Let's draw a little schematic here. We have the actual status. The person could actually be guilty, or they could actually be innocent. So this is, if we were omniscient, did they actually commit the crime or not? Again, in the hypothetical no gray area legal system. Our test, our trial, will result in a claim that they are either guilty or that they are innocent. Let's just go with innocent for the time being. So we have four quadrants. If our trial says guilty and the person is actually guilty, that is a success. We've successfully identified a guilty person as guilty, and that's the goal of the trial. If the person is innocent and the trial declares them innocent, again, we'll just use that for now. People that know more about the legal system might be annoyed by the terminology, but we'll clean that up in a minute here. But if the trial says innocent, they're actually innocent, that's also a good result. That's a concordant result with reality. It would be really nice if anytime we did a test, the results were always concordant with reality. Of course, that's not always the case. If our trial declares the person guilty and they're actually innocent, this is an error. We would like to not be in this quadrant very often. And similarly, if our trial declares them innocent, but they're actually guilty, this is also an error. We would also like to not be in this quadrant very often. Okay, so now we have to introduce the idea of a null hypothesis. So these two ideas, that the person can be guilty or innocent, are our hypotheses. Now, something that I might realize in a practical situation is, let's say that my test or my trial is kind of, operating in a sense on a continuum from innocence to guilt. We might go through the trial, and maybe as a result of the trial, I'm very convinced that this person is innocent. So maybe I end up like over here and I'm quite convinced they're innocent. Or maybe we go through the trial and I end up over here and I'm quite convinced they're guilty. But I also could end up kind of in the middle where I'm like, I don't know, they could be innocent, they could be guilty. I'm not really sure. What maybe I shouldn't say, I was going to say what I really should do. Like, maybe not what I should do. There's not a moral component here, I suppose, but at least one way to resolve this is to say, okay, I'm going to actually set up a default or a null hypothesis. I'm going to set basically a hypothesis that wins the ties in a sense. So I need a null hypothesis. This is kind of the default. It gets the benefit of the doubt. Or loosely speaking, it wins the ties. If we look at the evidence and we say, I'm not really sure, this is the one we're going to go with. We have to make a decision. We're going to go with the null hypothesis if we're not really sure, if kind of the evidence is tied in some manner of speaking. Versus the alternative hypothesis. This is often what we're trying to prove. And we set a high bar to establish that evidence. Set a high bar to establish this proof. Well, that was my pad is slipping around on my desk for some reason, more than usual. Uh, that was quite messy, so sorry about the bad handwriting there, but I wrote sets a high bar to establish, quote, proof. So what is my deal with my writing pad today? Okay, so in our legal system, what do we set as the default hypothesis? Well, we set as the default the person's innocent, right? You're innocent until proven guilty. So let's come over here and let me actually switch these around. My tech is just not cooperating with me today. There we go. So I have this innocent. I'll call it the null hypothesis, and I'll denote it with a capital H subscript 0. So the null hypothesis gets denoted by H subscript 0. So this is either H0 or often called H naught. So this is H naught. And a UGHT, like nothing, or like the word for 0. And our alternative hypothesis often gets denoted as H1 or H subscript A. I don't particularly like the H sub A notation because, well, number one, like H0, you think the subscript should be a number, but number two, actually little a, especially in small type, tends to look like a 0. So it's kind of really hard to tell them apart. So I call them H1 when I'm labeling alternative hypotheses. So in other words, if our test says that we're pretty sure that a person is innocent, we declare them innocent. If our test says we're pretty sure that a person is guilty, we declare them guilty. If our test says we're not really sure, we revert to the default, to the null hypothesis. We declare them innocent. So that's important. Now here we get our first kind of little nuance that pops up. Do I really declare them innocent in that gray area? If I say like, I don't know, they might have committed the crime, but they might not have, I haven't really given evidence that they're innocent. I've simply failed to provide enough evidence that they're guilty to call them guilty. It's in the gray area, right? Maybe I'm even pretty convinced they're guilty, but not quite at this high bar, right? Maybe I'm like sitting right here, but not quite convinced enough to declare them guilty. But I certainly wouldn't say I think they're innocent. I think they probably more likely to be guilty than not, but not more than a reasonable doubt. So maybe our trial, so in actuality, we can call them guilty or innocent if we were omniscient, but maybe our trial should actually be calling them guilty if we're very convinced they're guilty, or actually maybe not guilty if we're either convinced they're innocent or we're not really sure. So we're actually going to call this not guilty. So in either of these two situations to the left, the we're pretty sure we're in it, they're innocent situation, or the we're not really sure, either way, we're going to call them not guilty, because really this is the bar that's important. Are we calling them guilty, in which case they're convicted of the crime and get the sentencing? Or are we calling them not guilty, or have they not met that bar, in which case they go free, regardless of whether we're really sure they're innocent or whether we think they maybe aren't guilty or innocent, we're not really sure. In either of those cases, they're treated the same way, they go free. Okay, so we cleaned up that little bit. In actuality, the person's either innocent or guilty. Our trial results in either guilty or not guilty as the verdict. But if we declare a person who actually is guilty as not guilty, we've made an error. And if we declare a person who's actually innocent as guilty, we've also made an error. So if I think about my hypotheses now, the person being innocent is the null and guilty is the alternative hypothesis. So in my top right corner here, if I make the error by calling the person guilty when they're actually innocent, I reject the null hypothesis, I reject the default of them being innocent in favor of the alternative. I call this a type 1 error. And it gets labeled with a rate alpha. This is actually a similar notion of alpha to the alpha that we used in confidence intervals. When we talked about hypothesis testing, we had like a Z alpha over 2 kind of idea, that error rate being alpha, similar idea here. On the other hand, if I fail to reject a truly false null, if I declare the person not guilty when they're actually guilty, if I don't reject the null hypothesis when they're guilty and the null hypothesis is actually false, I've made an error there as well, and I call that a type 2 error. And that gets a rate beta. So these are the first two Greek letters of the Greek alphabet, alpha and beta, where the word alphabet comes from, alpha, beta. So our type 1 error with rate alpha, type 2 error with rate beta. We're going to focus a whole lot on alpha as we go through this development. We're not going to talk a whole lot about beta. It's actually kind of hard to get a handle on beta. You know, what size it is, what number it should be, and so on. But alpha is really the important of the two for most of our discussions. However, it is important to note that there is a kind of a seesaw relationship between alpha and beta. If I push alpha down, beta pops up, all else equal. Or if I push beta down, alpha pops up. Of course, if this wasn't the case, then I would just push them both down. I'd choose to set up my test so that both alpha and beta are essentially zero. And then I have a really good test. It just declares guilty people guilty all the time and not guilty people not guilty all the time. And there you go. So of course, practically speaking, that's not going to really be feasible. And so we have this trade-off, right? For me to get a low type 1 error, that means I have a higher type 2 error and vice versa. Now, all else equal, that's true. Sometimes maybe I'm able to do more work. Maybe if I'm taking a sample in a less abstract type of setting, if I'm taking a sample, maybe I can take a bigger sample size and actually be able to decrease both of the type 1 and type 2 errors, but then that's more costly, right? I'm doing more work, I'm taking a bigger sample size. So there's no free lunch, just like in most things in the world. Okay, so to recap, H naught and H1 are the null and alternative hypotheses, respectively. H naught, the null hypothesis gets the benefit of the doubt. It kind of, in a sense, wins the ties, or it's uh, the prevailing worldview. H1, the alternative hypothesis, this is what we're trying to show evidence in favor of. So we're actually setting a pretty high bar for ourselves, saying that to substantiate the claim that I want to make, I've got to actually surpass this bar here. I can't just be in the gray area. That's not enough for me to make the argument that I want to make. I've got to actually pass over into the territory where it's clear and convincing that uh, that the null is incorrect, right? Kind of like the 1,000 to 1 odds ratio, or 1,000 to 1 odds, where the guy was saying, okay, you can dig in your heels and insist that flex time has, or that absenteeism has not gone down, but that there's only a 1 in 1,000 chance of that. Okay, so we presume the defendant is not guilty, and we only declare guilt if there is significant evidence to overturn the presumption of innocence. In our legal system, we would call that evidence beyond a reasonable doubt. And this beyond a reasonable doubt statement would kind of be saying something about what we think the size of alpha is, kind of roughly speaking. If we fail to prove guilt, that's not the same as saying we have proven innocence, right? We set a very high bar. We didn't meet that high bar, but we could be in the gray area. Maybe the result of the trial makes the jury very convinced the person's innocent, but maybe the result of the trial makes them think, well, the person's probably guilty, but there is enough reasonable doubt that we can't declare guilt. And there are two main ways to make an error, type 1 and type 2. We can declare an innocent person guilty. This really should say declare an innocent person, because their actual status is innocent. We could declare an innocent person guilty, or we could declare a guilty person not guilty, or treat them as though they were innocent. So our type 1 error, rejecting a null even though it's true, this is called the significance level and is as given rate alpha. Our type 2 error, failing to reject a truly false null, this is given the notation beta. And sometimes we call we refer to the power of a test, the ability for it to tease out truly false nulls. Sometimes we call that the power, and that's 1 minus beta. And as I mentioned before, kind of in a perfect world, both error rates would be 0. We would never be in either of these error quadrants. We'd always have just a perfect test. But we're not in a perfect world. We don't have, we're not omniscient. So in reality, where there's a trade-off between alpha and beta, pushing one down increases the other one. And really the only way to decrease both is to do more work, for instance, taking a larger sample. And in our society, at least so we claim, maybe not true in reality, but so we claim, we typically want a small alpha at the expense of a higher beta. we think that it's worse to, say, imprison an innocent person than to let a guilty person go free. At least that's what we write in textbooks, right? Whether that happens in an actual jury or in an actual instance is certainly highly debatable. However, note that it's not necessarily always the case that a small alpha and larger beta is preferable. For instance, in a screen for a disease, the opposite is often true. Where you know, the null would be the person does not have the disease, and the alternative would be they do. And in a screen like the types that we saw in the Bayes theorem chapter, well, we often saw that if you come up positive for a disease on a screen, the chance that you actually have the disease is still pretty low. But the thing is that, you know, missing a person who actually has a disease and letting their disease progress for another year or 2 years before it's caught is, you know, probably on balance most of the time a lot worse than uh, telling a person that you saw some suspicion for a disease and that they might want to go for a confirmatory test, and then them finding out a couple weeks later they actually don't have it. Right. So in say a medical screening example, we might be much happier to accept a higher alpha to keep the beta very low, so that we don't miss true positive patients. So we don't miss very many patients with disease and let their disease progress untreated. Okay, so why is the logic complicated here? Something that I've glossed over is, well, why did we put the person on trial in the jury? We put them on trial presumably because we suspected they're guilty, right? And in a sense, I'm trying to prove guilt, right? We think the person is guilty. That's why they're in the courtroom. We don't just take random people and put them in a courtroom. At least, you know, again, ideally, we don't do that. So we think the person is guilty. So we think they're guilty. So we presume they are innocent. We presume that we are wrong. And then we try to provide evidence that surpasses this high bar to declare them guilty. It's kind of backwards logic, right? Usually we would think if I think a person is guilty, I'm just gonna directly attack the guiltiness, right? I'm gonna try to say, here's evidence that means that, you know, that means that there's a whatever 95% chance they're guilty. That's really not what we're doing here. What we're doing is we're saying, I think they're guilty, so I'm going to assume they're innocent, or presume they're innocent, maybe is a better way to say it. I'm going to presume they're innocent, and then I'm going to present evidence that basically shows that it would be very silly to continue insisting they're innocent, and it makes much more sense to switch to them being guilty. So I'm actually starting off assuming the opposite of what I'm trying to prove, kind of roughly speaking, and then trying to argue against the thing that I've assumed. So I kind of start off by presuming innocence and then attacking innocence and showing that it would be very silly to continue insisting the person is innocent in light of the evidence. So really, hypothesis testing takes kind of a backdoor approach. It's an argument by contradiction in essence. I'm saying the opposite of what I want to show to be true is silly and cannot be true in light of the evidence, roughly speaking. Okay. So that's, I think, one of the things that makes hypothesis testing difficult is we're taking a very, you know, whatever, beating around the bush almost approach to proving this, where we start by assuming the opposite of what we want to show, and then we kind of like attack that assumption and try to argue that it's silly, and therefore the thing that I want to show originally is the thing that we should conclude. Okay, let's take a look at an example. We only have about 12 minutes left, so we probably won't get all the way through this. We're actually going to solve this example in 3 different ways. That's, I think, another thing that makes hypothesis testing a little bit challenging, is that we have multiple tools in the toolbox, so to speak. We can attack this via a p-value method, via rejection region method, or via critical value method. And sometimes one method is better than the others. They all will get you the same answer. So if one of them gives the answer, reject the null hypothesis in favor of the alternative, the other ones will give you the same answer, but they give you different additional data along the way, different, kind of ancillary points that you can use to either understand things in a little bit more detail, or maybe to answer closely related questions that you might also want to ask. Okay, so we're going to start off with the z-test for mu. So here we're doing a test for the mean. Now we're actually moving into something a little more tangible. We're moving away from the abstract idea of jury trials and things like that. We're saying, okay, I want to know what mu is. I would like to know the value for mu, or at least something about it. Now, to start with, if I knew what mu was, if I had access to the population data and I could just compute mu, I would compute mu and I wouldn't have to do all this silliness in chapter 8, hypothesis testing. So we're of course presuming that we do not know mu, but we instead know x bar observed. Also, if we think back to confidence intervals, when we were developing an estimate for mu, we kind of had two scenarios. Did we know sigma, or were we estimating sigma by s? The z-test for mu is going to be when we know sigma. So here sigma is $1,100 and it's known. So that's the context we're in here. This very closely mirrors the confidence interval idea. The z-interval for mu was when we had x bar observed and knew sigma, but did not know mu. Similar idea here. Okay, so what's the rest of this example? All right, it's reported that the national average credit card debt is $3,262. A certain college believes their students have less credit card debt than the national average. Maybe they would like to make this statement in their marketing material. They take a sample of students and they get the following information. Sample size of 50 students resulted in a sample mean credit card debt per student of $29.95. And we'll suppose we're using a known standard deviation sigma of $1,100. And our question is this: at the 5% level, can the college make the claim? In other words, can we put this in our marketing materials? And if another competing college comes to us and says, hey, I don't think that's right, can we show them this sample along with our logical argument, just like the guy with the flex time, right? He kind of gave the sample statistics and then gave a logical argument to support his conclusion. Can we give them the sample and our logic and say, this is the substantiation for this claim? This is why we can make this claim, and this is the evidence in favor of it. We're not just saying stuff and making it's not false advertising. We do have evidence for it. Okay, can we make the claim? Well, let's first, I think in the last 8 minutes here, we're not going to tackle any of these three, but we're going to look at maybe three scenarios. Let me consider the standard error. What's the standard error here? Well, it's sigma over root n, or it's 1100 over root 50. And I know you can't see the calculator, and I'm just going to do this really quick on the calculator. 1100 over root 50, what does that give me? That gives me about 155. So my null hypothesized mean is 3262. This is kind of the default, right? If I didn't know anything else about my students, if I didn't have this sample, I would probably assume that my student's credit card debt is about 3262. That's the best guess that I have. But I have a sample from my particular group, my particular college students. So let's forget about this X bar observed for just a minute, and let's look at a few different scenarios. What if I had gotten X bar observed is 3,500. What's the claim that I want to make? The claim that I want to make is actually that mu for my students is less than the national average. Do I think an X bar observed for my students' population, a sample from that population of 3,500, is evidence in favor of my students' mean being less than 3,262? Certainly not. I'm on the wrong side of things, right? If anything, I'm showing evidence that the mean is bigger than 3,262. Can I make the claim? No, clearly not. What if we did it? What if, so not same college, we're not doing repeated samples here, but completely separate, erase the 3,500 from your memory. What if we had instead gotten 1,000? We take a sample of size 50 from our student body, and they have a sample mean credit card debt of $1,000. Remember, standard error is $155. This is a whole bunch of standard errors below the mean. I don't know how many, like, what, 10 or something like that. More than that. I mean, this is one of my grad school professors talked about the intraocular test, the hypothesis test where you look at it and it just jumps out and hits you between the eyes. It's like, yeah, this is obviously significant. If the national average credit card debt is $3,200 and a sample of size 50 yields a credit card debt of $1,000, yeah, our students have less credit card debt. We really don't need to run the numbers at all. Yes, very clear. Now, different scenario. Again, forget about the 1,000 now. What if instead we had gotten $3,260 for our X bar observed when the mean that we're comparing to is 3,262? I mean, we are on the correct side of things, but could our students' actual average credit card debt be 3,262 and we just happen to get, a couple students with a few dollars less on their credit card right now or something? Yeah, we're only $2 away on a standard error of $155. That's like nothing. So here, even though we're on the right side right as in correct, 3,260 is less than 3,262, but we still cannot make the claim. Why not? Could very well be due to sampling error. Well, I should actually say that could very well be due to sampling error. It's not necessarily due to sampling error, but it's not far enough away that I can be fairly confident that it's not due to sampling error. So then what about 2995? I don't know. I mean, it's kind of far away from 3,262, but it's not like really far away. It's on the correct side. It's 2095 is less than 3,262, so it's in the right direction. But it's not so far in that direction that it's clear that it's got to be significant that I can make the claim that it's not just due to sampling error. In this case, I need to do the calculations. So I need to actually worry about things like, what is my level of significance? What is my alpha? Is it 5%, 1%, 10%? I need to actually go through and do the mathematics, make the argument, do the calculations, and come up with an answer. So that's what we'll focus on next time. But I think it does help to look at some of these extreme examples to see where we can just kind of automatically, give an answer even without doing the calculations. We can clearly see, yes, we can make the claim in this case, no in either of these cases. this one's on the wrong side, this one's on the correct side, but it's really not far away at all. But this one's on the correct side. It's a little bit far away. Is it far enough away for me to be fairly confident that it's not due to just sampling error, that I just happened to get a lucky set of 50 students and, that was why this is lower than 3262? Well, we'll do the calculations and we'll figure that out next time. Okay, so that was our start on hypothesis testing. Again, strongly recommend reading through the first section of chapter 8 on hypothesis testing, on the logic and everything before next time. And that's what we'll continue with when we come back. So let me stop the recording.